Hello! So today we're going to talk about the fourth dimension. Now, from now on, I want to get things clear. When I refer to fourth dimension, I'm referring to a fourth spatial dimension that's perpendicular to all of the three we have now. So that's height, width, and depth. Now we add a fourth dimension. How do we show the fourth dimension then? Not like we have some equipment to help us visualize the fourth dimension. So let's go back. This is a computer screen, right? Know that the space around me is actually three-dimensional, but this computer makes it look two-dimensional so that you can watch this video that you're watching right now. So we have to sacrifice something. Unless this is a hologram. I don't think this is a hologram. Because if we put a point here, can't draw one, then there will be an infinite line of points that I could put the point on, and it would always look the same. So we have to sacrifice a bit of clarity to help us visualize this in a two-dimensional world. So for this video, I have a few questions you might want to think about and pause the video before you continue on. Or if you're just way too impatient, then you can continue watching. My first question is, when we can take a square and put it in and immerse the two-dimensional world it lives in into the third dimension? We can do that with a three-dimensional object like this eraser and put it and immerse that three-dimensional world into a bigger four-dimensional world. So what happens when we rotate the eraser not in our three familiar rotations, but in the three new rotations that the fourth dimensional provides us? Then we take a projection, basically shine a really bright light in the fourth dimension and watch the shadow like a shadow movie. What will it look like? Obviously we can only see, two-dimensional. So if we had a four-dimensional creature who could see in three dimensions, then what would it look like if he just focused on that three-dimensional space that our four-dimensional rotating three-dimensional cube is projected onto? Second question, what does a hypercube even look like? So now we can start with some explanations. First, I already defined what the fourth dimension we're talking about is, and there's one way, which is squish it. There's also another way. We have this plane, like this plane. Okay, that's imaginary. We shove an eraser through it. Every second, we produce a new image that's two-dimensional by looking at the part of the eraser that crossed the plane. We can also do that with shoving a four-dimensional object through three dimensions. Now that we've got stuff cleared up, let's look at some basic things. Chapter 1, Introduction. So to get a little used to the fourth dimension and how us three-dimensional creatures are trying to picture it, we need to get a little used to how two-dimensional people try to picture our three-dimensional universe. And I'm going to use Desmos 3D for a small demonstration, because Desmos is good. If you don't know about Desmos yet, DSMOS, just type in that and then type .com. You'll get some good results. Okay, how much time does it take for this thing to completely load? Okay, done. So you can see a pretty nice image over here. I'm going to delete this perspective thing first. And now we see two blue things. One of them is our cross-section of this lovely cube. Three-dimensional, passing through our hypothetical two-dimensional object universe. Dun dun dun. The XY plane. Guess you already knew that, perhaps by looking at the image. This is a perfect projection, just the right way to give us a nice hexagon. But of course it doesn't always have to be this nice. I can tweak this a little to rotate it. Let's play this rotation. Now observe how this thing distorts. But what's wrong with this? So as this distorts, we see this cube that's changing shape. So we think that if we pass a hypercube through our universe and rotate it, then it will also change shape. At least the cross-section will. We can, of course, combine other rotations to get even more complicated rotations. We also have this really nice slider that lets us translate this. Shift the moving cube. Or we could also use this which would move it up and down, which will change the cross-section completely. So this is a pretty nice simulation. I'll send you the link for this desmos graph in the description, but come on, let's get on. Well, this two dimensions is nice. That's only one half of the feature that we have. We also have this really nice object. When we look at it right now, it looks really three-dimensional. How did I do that? No, actually, no idea. Maybe it's just me. Okay, now it looks even more realistic. Looks like the blue is drawing a line and filling in for the silver part that's under the XY plane. But come on, the cube is making this look confusing. Let's see if we can destroy it. Hey, got the cube. So yeah, but it's completely smushed onto our two dimension. So this is a projection of our cube, even though it looks really realistic, like a three-dimensional cube. But of course, why are we using a cube? We can also use other weirder solids, I suppose. And I'll show you how, and I'll give you more details by showing you how I made this. So we just duplicated this. These are our vertices, these are our edges, these are our surfaces. That's really nice, right? This is the actual thing that's inside the cube. This is our vertices, but smushed onto two dimensions, as you can see. Even though, come on, it looks really realistic. But did you notice something? If we tilt this, then it looks like we can distort the cube. I wonder why that is. If you have a solution, then post it in the comments. We also have our edges, xy. Also looks like it's distorted. And we also have our xy surfaces, which give us the actual cube, the stuff inside the cube that is. Also looks very, very realistic. We also have our cross section, which looks really weird. I have no idea what it's doing. So perhaps this will help us visualize. But to a two-dimensional person, they don't know about this, this, and this. All they know is this, what's passing through their universe, and like a rough shadow of it. And they also don't really know the whole thing, because we three-dimensional creatures have a two-dimensional plane of view. So they two-dimensional creatures must have a one-dimensional plane of view. Even though by looking at different angles and being able to stop it and start it whenever they want, they could build up a pretty nice picture. They just wouldn't know what was the inside until they go in. Also, this thing looks way too realistic. However, we don't need to do that. We can also have other better or worse vertices. Because this is pretty constricted. So this is a skeleton of our cube, and this is a cross section. Why a cube? Why not do something else? Because we could change this. Here we just changed one vertex. See what happens if we follow it along. So then a bunch of other changes into other vertices. But that's only one part. Our section is based on a completely different part, even though the edges change a bit and look realistic with it. So yeah, let's add something. X length 0. Just kidding. It's 5. It's 2 actually. So this is basic desmos stuff. You can probably ask the desmos team how I do this. However, the real good part comes when I try to use this to make this three-dimensional object. So we start with some basic sliders. Now it has 2 parts. The first part, all these vertices, they determine exactly one part of this. Again, basic desmos stuff. If you don't know how to do it, then ask those nice desmos people. These are our parameters for the points. Pretty good. So all these do is that our G1, for example, just gives us the basic point. Then f is a function that takes in the point in 2 rotation angles and spits out another point, which is basically the first point. But the point has to be in xy coordinate form or else it won't work. Rotated by the 2 rotations. You can probably tell which direction we have to rotate it in. And of course, we can do the same thing we just did with all of with a different coordinate to elongate that coordinate too. What's that be? But that's also zero. Anyway, now we can do that with a third coordinate to finish that off. After that, the actual fun begins. Yes, I could stop the recording, but it's a lot nicer to show you how it's actually done. And of course, to see the whole picture, you sometimes need to zoom out. This is our second part. This is these are the edges. It basically connects all of these.
It's 15.
And these are the surfaces because the only things we can do are triangles. I had to make the squares out of triangles. And this is a constraint for the section. Well, another function g is basically the inverse function of f, except that these three coordinates are in a different order, and these two locations are in the reverse order. So we have to adjust this a little. Of course, it's sort of annoying when desmos shows some error messages like briefly, because under these things, which lag pretty often, it's sad. And h is our third function, which projects our 3 dimensions down to 2 dimensions. We could do it a couple of ways, but I like 2 really good ways. One is to just zero out the third dimension, and the second way is just to make the third dimensional concept and how far away it is, and then use some perspective. First, we do edges, and then we do surfaces, just the same way. And then this is the other interesting part. We need z to be 0, but we still need these to be interesting. So we make it a basic constraint, but also make z 0. So we can make it a bit better. That's a really annoying part. So that's how we make this. And now that you know how we make this, you might have a little insight into how we make our, well, 4-dimensional objects. We keep cutting through 3D. So yeah, that's the end of chapter 1, our fairly long warm-up. Chapter 2, the actual 4 dimensions. This is the animation of 4 dimensions. The 4-dimensional hypercube slowly rotating. Except that it's not a hypercube because this is a 3-dimensional calculator, not a 4-dimensional one. But yeah, you get the point. It's a projection of a hypercube. I turned on the ticker to make it slowly rotate, because whenever I try using the sliders, it rotates too quickly. So this is the 4th dimension. I turned on perspective, but I can easily turn it off. In fact, we might want to. Leave it with no perspective on first dimension x, no perspective on y, and no perspective on z. It's a lot bigger. So have to wait, what happened? Do not. And now you can actually see the two cubes which are linked together. Maybe not. And there's that one beautiful moment where the two cubes pass right over each other. And of course I can show you that in 2D, but it's already intuitive enough. I mean, if it isn't, then just play around with my calculator, which I'm going to post in my description, and also this one. And if it is, then still do that. Of course, this is made in nearly the same way. Where W1 is, of course, the offset in the W dimension. These are the vertices, except that desmos doesn't support 4 points with 4 corners. If they do, then please tell me, because I never tried. So I had to use lists with 4 numbers. Except that I can't actually draw the hypercube, so I just use the projection function h. Also the rotation function f and g help me rotate. I just use the projection function h to help me project this 4-dimensional 4-component list to a 3-dimensional point. Desmos is going to make a 4-dimensional calculator soon. So yeah, we just have to stick with this. This is a long list of all the faces. In fact, when you look at a hypercube, there's like 2 types of faces. So for now, we'll separate it into 2 cubes. Of course, each of the cubes have their own 6 faces. So that makes 12. But you can also make a face by taking the edge in one cube and taking the corresponding edge in the other cube and putting them together. And since there's 12 edges in a cube, that adds 12 to the total for a total of 48. Of course, it can make some weirder projection functions. Or maybe one that was perspective, but from the perspective of the center. This one is very dumb. So this is a projection except that it's divided by the distance from the point to the origin. Nice way to make perspective. Except that it makes this whole thing an awful lot smaller. Is that actually how we see perspective? Yeah, farther away things get smaller. So yeah, this is our perspective cube. Good job, like. This current section was made in pretty much the same way. Just anti all of this. But that it takes an awful longer amount of stuff to write. You know, I've also shown these faces, but this will block an awful lot of stuff. It also looks surprising when one edge or one vertex emerges out of the face, which is not the effect we want. Of course, I'll send you the link in the description, so if you do want it, then yeah, go for it. Notice how at most of this it just looks like most of the stage it just looks like a normal cube until the inner cube starts to pop out. But then the four farthest away corners go back in, and then it looks like a cube again. Not until you remove the surface of that leaf. Also, desmos didn't make a pyramid function, so I can't really do this well. And also, our puzzles. This is what a four-dimensional hypercube looks like. Except in 4 dimensions. We could go all the way up, down a few more dimensions. Come on, this project is already slow enough. But if you do want that, I'm going to do it a little later. Anyways, back to our question of rotating 3-dimensional cube in the 4th dimension. Save this. I really like my new projection function a lot better. Also, don't ask me where I got so many desmos graphs. This one. The inside out 3-dimensional cube. Hello, welcome to Foreign Channel. This is a normal, ordinary 3-dimensional cube, but it's rotating in the 4th dimension. Which causes this weird distortion to happen to it. Of course, we could have picked differently. We could be different. Right there, it looks like a perfectly innocent cube. But what just happened to it? It's rotating. It's a little hard to keep track of. Also, the part that looks like it's the outside, but then it suddenly becomes the inside. I mean, it looks like it's the inside, but it's actually the outside. That part is really weird. Also, I turned on consistent surface here. Did I? Oh no? Then bring it from now. You can actually look inside the cube. Well, this doesn't make it clear. I don't think it's really helpful. Of course, we could have picked another pair of points. Perhaps one that was more interesting. But yes, sometimes when we rotate a cube like this, it just starts to look weird. Of course, as we all know, sometimes it doesn't. This is not the only possible result. This is just a minor distortion. But of course, there could be other results. If we chose a different cube to watch, then we would see the cube go through itself. Probably more interesting for a movie theater. So we'll think of it like this. We have a model of a 3-dimensional cube. To see what I mean by there's a possibility that the cube can go through itself, we need to look at a two-dimensional model again. So you might have noticed, if you're really clever, that this is exactly the thing I used for the warm-up. But now I've turned off the plane, turned off the cross-section, turned off everything to make it just look like a normal, innocent, three-dimensional cube. And now I'm going to highlight one surface. No, not that. Come on, turn off surfaces. So watch this surface as I rotate it. You know what, I'll just turn it on auto rotate. This rotation just distorts it a little, but doesn't do anything weird. This rotation, however, you can find a time where, I'll make it even more clear. In this situation, in this rotation, it clearly looks like the square, or quote-unquote square, that's distorted by our 3 dimensions. The square, it's passing through itself. And suppose we remove all the faces in all the parts of the cube except for this square. Now it's a 2D object. And of course, it could go through itself if we rotate it just the right way. But I want to explain to you how it goes through itself. The rest I'll just leave for later. So, just think about it first. Okay, if you don't want to think about it, fine. The 4th dimension gives us extra space. You can change your 4th dimension slightly, go through any wall, because it's not. Say you're trying to navigate a 3-dimensional world, but you're stuck in a room. How do you get out? Well, if you could change your. If you could move in 4D, then it will be easy, because a wall only exists in 3D, but you can move through 4D. Let's change your 4th dimension coordinate bit. Okay, now the wall disappeared because you're not in that same 4th coordinate. So now just move to a different room. Okay, now change your W coordinate back. Congratulations, you've teleported across the wall. Now suppose that you are a wall. You can do the same trick to get across this wall. Now make a cube. This wall is 4 of the point, and this wall is a different 4 of the point. People wouldn't really call this a cube. Now, this is an animation of your teleportation trick. Projected onto 3D, of course, where your 4th dimension is effectively zeroed. So, there will be a really weird point for someone watching in the 3rd dimension when you seem to go through that wall. But in fact, you're not going through that wall. It's just that you're going through a 4th dimension of what would have been the wall. So that's basically what's happening with our square going through itself. It's actually going through what would have been itself, but was in 3 dimensions. Same thing with our cube that could have gone through itself, except that it didn't want to. Okay, so also I want to talk to you about this really weird thing, which I'm going to mainly leave for part 2. We have this square. We have 6 ways to glue it together. Well, at least people say there's 6 ways. There's a few more, because You don't need to make opposite sides correspond. If you read the book Things to Make and Do in the Fourth Dimension, then you know those 6 things. A disc, a cylinder, a Mobius loop, a torus, a Klein bottle, and a projective plane. P.S. I tried making all of them using paper. The first 3 turned out pretty well. The 4th one turned out okay. The 5th one turned out not that good. The 6th one ended up as a total disaster. When the thing appears to go through itself, it kind of got around this problem by existing in 4D. By doing that same teleportation trick I showed you, this thing teleport here, but going through the 4th dimension, the 2-dimensional object could have also popped out into 4D and gone across that thing that it went through. And that would be a real Klein bottle, except that we're stuck projecting it onto 3D. And as I explained earlier, when you try this teleportation trick but project it onto 3D, it looks like you're going right through the wall. So it looks like that 2-dimensional surface is going right through the other 2-dimensional surface. And that's it. I'm going to talk more about some interesting phenomena in part 2.